Howdy diddly do. So Huggingface just released this NLP library right here. And this is pretty cool because it allows you access to about 100 NLP datasets and 10 evaluation metrics pre-packaged. So knowing Huggingface, this is going to be a breeze to work with. So what I thought we would do is we would try to use this. I have not used this yet, and it's been a while since I've used any Huggingface stuff. So what we're trying to do is use this to load up the IMDB dataset and then use a BERT model maybe to build a sentiment classifier on top of that using PyTorch, specifically PyTorch Lightning. So all of that combined from scratch, and basically if I can do it, then so can you. And we're going to make some mistakes and have to look at the documentation a bit and so on. But that's the process, okay? So first of all, if you like content like this, let me know. If you're not subscribed, subscribe. Let me know in the comments if you have any sort of criticism or tips. I'm always happy for Vim tips, honestly. So I have a pretty empty Git repo here. I have a git ignore, but that's about it. So we'll just dive right in. Start up Vim and let's make a file. So first, some boilerplate code. I'm terrible at talking and coding at the same time, but you know. So I like to use this Apsel library, and I'm using, as you can see, I'm using the Tab9 completion engine with COC with NeoVim. This is absolutely great. We maybe need app flags logging. That sounds good. So we'll need Torch probably, right? And we'll need PyTorch Lightning. Torch Lightning as PL. We'll need the NLP library, of course, since we're going to use that. And we'll need the transformers library. Now, I know Huggingface has this tokenizers library too, but there are some tokenizers in the transformer library already. And we'll just keep it light like this. So maybe NumPy, maybe not. Let's see. So we'll have these flags object here. Maybe we'll do some flags later. And the main function, let's just call hello. Actually, let's log that info. And all right, run main. So this is our boilerplate, and let's just quickly try it out just to see whether it works. So here we are. Hello. That's fine. All right. So where do we go from here? So in PyTorch Lightning, what you'll have to do is you have to build this kind of model class, right? So we'll build an IMDB sentiment classifier. And that's going to extend this Lightning module of PyTorch Lightning. So you need different things in the PyTorch Lightning module. First of all, you need the init, and we'll just do like a very basic init. We'll call super on it, and that's about it. And you need a forward method, since this is a module. So in the forward method, you're gonna get a batch, and you have to do something with it. And what we also need is a training step method. Training step, which gets a batch and a batch index. And we'll have to output some kind of loss or some kind of training procedure. Then we'll need a train data loader. So all of this you can look up in the documentation of PyTorch Lightning. Basically, you implement these methods and it will do the rest for you. So it will do all the training loop, and it will do the handling of GPUs and whatnot, and the whole looping over epochs. All of that is basically taken care for you when you use PyTorch Lightning. So last thing we need is maybe a prepare data. Let's put that more up here. Prepare data. That method is optional, but it gets called at the beginning, and that's going to be pretty good for us. So I have downloaded the weights of a BERT model and the data set, so we don't need to do that anymore. Yeah, so that's about it. And I am going to, so maybe I've forgotten something. Lightning examples. Here's what we're going to do. We're going to look at like an example of PyTorch Lightning, and just to see whether we'll have it. So maybe here, domain examples, ImageNet sounds good. So we'll have these methods. This is way more than we need. But down here, so basically what you do is you instantiate your model, and we won't have these hyperparameters here. These will be our flags. But then you'll implement this trainer, and then you call fit on the model, right? Okay, so let's maybe copy this down here. So we'll model. This is our IMDB sentiment classifier, and the trainer. The root here, let's call that logs. GPUs, we'll give it a GPU if CUDA is available. Else 0. And then we'll make a flag for the epochs. We don't need the rest of this. And then at the end, we'll call fit model. Okay, so if we had a classifier, this would already run. Cool. Now, what I like to do is to have this module called sh, which gives you some sort of easy shell commands. And at the beginning of each run, whenever the file loads, I just do I remove the logs folder. So I have basically a clean logs folder, and then I make it again like this. So it just deletes the logs and then runs them again. So if we run this right now, this is gonna give us an error, probably. Okay, so we don't have an epochs flag, right? So we need to define a flag. Let's call define integer. Yep. And we'll go for 10 epochs right now. Cool. Okay. Very cool. Okay, so we haven't configured our optimizers. So in PyTorch Lightning, you need some sort of optimizer configuration, and we'll just copy that from an example. Going full Siraj here, people. Okay, so we need to configure optimizers, and I like the SGD for this. SGD tends to work well in neural networks. We don't need the scheduler. We don't need any of that. So let's just return the SGD optimizer with the parameters, and we'll make a flag for the learning rate, and we'll make a flag for the momentum. Okay, we don't need any weight decay right here. Cool, let's put these. We'll make floats for the learning rate. Maybe start off with something like this. So I never put help strings if the description is rather clear. Only losers need help. Like, don't be kidding yourself. If you put a help string, you need help. That's how it works. All right. So I just don't like that this library forces you to put the help string, because it somehow makes me feel bad. Because it's very opinionated, right? It says basically, well, you should put something there. Okay. So we have this, and now when we run this, we don't have anything to optimize yet. So first of all, we need the model, right? Do we need to prepare data first? Let's check. So I have this short thing snippet here that embeds an IPython shell, and I just plug this into anywhere so I can see if I reach it, right? So I reach the prepare data. So let's care about the data set first. This is why we're here, right? So this NLP library, as you can see right here, maybe, so there's the usage right here. So you can load a data set here with the, I think even with the appropriate split, and it will basically just give it back. So if you don't have it, it will download it. It's pretty cool. So we'll just load the data set, and I've already sort of checked out what they have, and they have the IMDB data set. Okay, and in this split argument, we can say, give me the train split, and as a string, you can say, give me whatever, the first 5% of the train split. Since we won't be, like, this is just my laptop here, so we won't be able to train like a super high grade model. But we'll go for 5% of the train split. So this is the train data set, right? And now if we run until here, so if you had not downloaded this, it would download this. So given the train data set, I hope you can see this. So it says it's a data set. It has 1,250 rows, and it has, each entry has a text and a label. And if you look, you can just index this like a data set, and that's the first sample, right? So the label is 1 here, means that we should predict the label that this is a good sentiment, right? It's either 1 or 0, maybe, yeah, I think so. So either good sentiment or bad sentiment. Okay, so our first task is going to be basically to get this into a form where BERT can consume it. So how do we do this with this NLP library? And that's the pretty cool part. So right now you see this is text. So in NLP, we need to map this text into token IDs. So we need to tokenize, and we need to map this to IDs. And Huggingface, of course, has very nice libraries for that. They're called tokenizers. So we'll have one of these tokenizers, and we'll use this from the transformers library. And I think this is called BERT tokenizer, that then the BERT models can use. Let's check it out. Okay, we're at the documentation. So BERT tokenizer. There we go. There's a BERT tokenizer. Fast. Ooh. Yes. Okay. We'll take the fast one. Maybe not. Yeah, we'll take the fast one. Come on. Be risky. BERT tokenizer fast. And I think we can do this from they have these methods from pre-trained. Yes, right. So we'll take this from pre-trained, and we'll put the model name here. Now, I want to make this a flag such that I'm not bound to a particular model. Oops. Cool. So this is called model. So this is our model, the BERT base uncased, and we have a tokenizer right now. So what we can do is we can now tokenize these things, every entry in the data set. Now, in a classic setting, we'd have to, write a loop for that. But with this dataset library, with this NLP library, it's pretty cool that we can tokenize basically each of the samples. We can map this tokenizer function across the training data set. So how do we do that? We have this tokenizer, and the tokenizer has, I'm pretty sure it has like a tokenize or an encode or something method. So there's forward. No, this is the BERT model. Where's the BERT tokenizer? Right here. Right here. Okay, it has, pretty sure it has this encode or something. Here, oh yeah, encode, right? Encode. Where is the definition of that? Can we click on this? Okay, cool. So this encode takes text and it takes a bunch of other arguments, such as, I hope you can see this. There we go. Such as whether or not you should add the special tokens or the max length. This is going to be pretty important. And pad to max length. We want everything to be of the same length. So if you apply this encode function to a text of these samples, so let's just take the first sample here and let's take the text entry. Then what you're going to get is like a list of these IDs. This is exactly what we want. So the 101 here is this CLS token that BERT takes in, and then it's just the word pieces, right? So you could also say, instead of this, say tokenize, I think. And that will just give you the word pieces, not the encodes yet, right? So these are the word pieces right here. This is the tokenized text, and with the encode function, it does this and then maps these to IDs such that BERT can consume that. So for this, NLP, this library has this convenient function called map in their dataset. So what we'll have to do first is we'll define a tokenized function that takes in a single sample, and then it will run the tokenizer encode function across the text entry. And we have already seen we need like, so add special tokens is true. This is cool. With max length, yes. And we'll make a flag sequence length or something. And we are going to pad to max length is true. So every single sample will be of the same size. Now in this function, there's a number of ways what you can return here. So one way is to return the original sample and actually just set a new attribute. I think set a new attribute on this original sample right here. Let's format this a bit nicer. So you see we have this tokenized function. It takes a sample, it takes the text, it tokenizes it, encodes it, and puts this as the new attribute input IDs, and returns it again. And now what we can do is we can map this function across the training data set, like so. So this will go over the training data set and basically for each entry do this thing. So hopefully after this operation, we'll have a data set where each sample not only has a text and a label, but also a input IDs attribute. And we don't have this sequence length thing right here, so let's put that here. Let's just go with 32, since this is just my laptop, so 32 samples should be fine. So here it says can't pickle tokenizer objects. So what it tries to do right here is it tries to parallelize basically this thing right here. So if we look at this NLP thing, is there documentation to this? We can just look at the data sets, maybe. Naming, splits, builder, arrow data set, map right here. So this function, I think it will try to multi-process, and therefore it needs to basically pickle all of the things that go into the I can't speak today. It pickles all of the things that go into the function, which means this tokenizer right here, it needs to be pickled. Now, maybe we can keep in memory, load, blah, blah, blah. Maybe there's a way to get around this. So one thing we can try is we can try another tokenizer. Maybe this one can be pickled. The still library is pretty good, but it can't pickle everything. Yes, so this tokenizer can actually be pickled. In the other tokenizer, so I'm not entirely sure what you'd have to do, honestly, because I don't know the library. But what you could do is like make a thread or process local variable of this and basically make it a singleton in each process. And then basically in here, you call the function to get it, and it returns the already instantiated object and so on. If you really want to multi-process all of this. Anyway, we have this train data set right now, and you see the schema. If you can see this, the schema has been extended. So there is now text, there is label, and there is input IDs, which is a list of int64 things. That's pretty cool. So now what we can do, since this is still a Python list, right? This is still a Python list. Now, I know the tokenizers can already output PyTorch tensors, but that's kind of cheating. So we want to use this library right here. So we want the train data set. There is a method called set format right here. And you say type equals torch. And what that does, and I think you need to say which columns you want. So we want columns. Maybe we should get all columns. Can we output the text? So you can select from the sample which of the columns you want. And let's check it out again. For now, as long as we're just debugging here, I like to do a debug flag. So this is usually one of the first flags I do. It's define Boolean debug. And what this does is whenever this is active, I try to be as fast as possible. So there in this PyTorch Lightning Trainer, there's actually this fast def run argument, which does the same thing, but I can push it a bit harder with this debug here. So let me say this is like one, yeah. We'll just load like batch size samples if we are in debug mode. Batch size, we don't actually have a batch size argument yet, do we? If flags.debug else 5%. Okay, so we don't have batch size yet. We're surely gonna need that at some point. So let's go with a batch size of 8. Just because we can. So now if we run this in debug, if we run this in debug, we should, okay, yes, this needs to be a string. Shagaboom. Cool. So it says it's the fast def run, and if we run it in debug, it just loads very few data points, so this map function here doesn't take this whole while. Maybe there's a way you can stream that, I don't know. For now, this is pretty good. So if we look at the train data set again, you can see that it has the same entry. So this is still a list of 64, but if you index it right now, if you go to the 0th data point, okay, then it crashes because it tries to convert these to PyTorch tensors, and it can't convert the string. So we'll have to say we just want the columns input IDs, and we want the label. Label, I can't spell. Okay, let's try it again. So right here you see that what we get out is actually a PyTorch tensors for this, and not kind of Python lists anymore. So this is now this is one-to-one, so with duck typing, maybe it's even subclassed. This is a PyTorch data set, right, which we can load into a data loader. So this is a perfectly fine data set. So we can now say self train data set is this train data set. Now we want to do this for the test as well, but in order to do that, we would have to write all of this code again, which I'm not really in the mood. So we'll just loop it. We'll create a function prepare dataset, and we'll take in the split name, right, like this, and we'll just go with the split name here. That should do it, and we just call it dataset. Dataset. Shakaboom, shakabang, shakaboom, and return that. So now we can say train dataset self.test dataset is prepare dataset for train and test. Okay. Excellent. So now we have a training dataset and a testing dataset. So here in the train data loader, we need to take the training dataset and construct a data loader from it. This is super, super easy. So what we'll do is we'll do it in one line. Data loader. So what does the data loader need? The data loader needs a dataset. So the prepare data is called at the beginning. So we have this data set right here. And I think we can go with a batch size right here. And we already have a flag for that. And I think there is like a drop last. Yes. So the drop last will go for true. We only want full batches during training. And we'll also shuffle. Okay. And the same goes for, we need a validation data loader for our validation set. So in PyTorch Lightning, you have train, validation, and test. And test is really only for like the final test. If the test data set we have here is would be called the validation data set in PyTorch Lightning. So we false here, false. We don't want to shuffle particularly. Okay, so we have a training data loader and a validation data loader. Now, what do we need? We have optimizer. Very good. Now, what do we need? All we need to do is to actually pass our data through the BERT model. So this forward thing here, we're just going to leave not implemented. Maybe. We can implement it. Okay. So we do need a model. As you can see right here, this batch, let's say this batch is going to, let's go right here, right? So if you sometimes don't know what to do, you just go to where you should be. Okay, at empty parameter. We don't have parameters yet. All right. So what do? We go up here and we make a model. We need to actually make the BERT model right here. So from transformers, we can use the BERT model. Now they have a lot of BERT models, and we'll go back right here to the BERT models, because they, as you know, BERT is just an encoder. So we need to build a classifier on top of BERT, but they already have done this. So they have a bunch of BERT different configurations. And the one we're looking for here would be this BERT for sequence classification, right? This is BERT model transformer with a sequence classification or a regression head on top, right? So this is exactly what we need, a classifier on top of BERT. And we can, I think we can also load this with this from pre-trained and just put in the same name. So we can, this BERT for sequence classification, and we'll load up the same model that we had. Okay, so this is our model. Easy as that. So what do we do with this BERT? If we put in data, what happens? For that, we have to quickly go back again. So in the forward method, we can input the input IDs, right? Which is batch size, sequence length, tensor. We can input the attention mask, that basically tells you where there's padding and where there isn't. Mask to avoid performing attention on padding token. Mask values selected in 0, 1, 1 for tokens that are not masked, 0 for tokens that are masked. Then we can input the token type IDs, which we don't have here. We just have one sentence, but usually in BERT you have the capability of inputting two different types, like a question and a paragraph, or a first sentence and a second sentence. Position IDs are optional. Blah, 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 blah. None of that. Okay. And we could also input the labels. These are optional, and it would already compute a loss for us, which we don't. That's almost cheating. So let's just focus on putting in the input IDs, and I think that's going to be enough. Since we basically truncate our long text to 32 tokens, we don't need to worry about masking right here. Otherwise, you would input a mask for, actually, we can do it. We can do it. Okay. So, what you could input a mask for basically where your tokens are not pad tokens, and the pad tokens in BERT are 0. So basically your mask should just be whatever's non-zero, but maybe also your model learns to ignore the pad tokens. I might be wrong here, and it does it automatically. Right, so in your forward pass, what do? Actually, let's go to the training step. We'll put something here. You can see it. So if you didn't have BERT, it would actually BERT you up. It would download BERT right here. But since I have it, you can see here, this is the smaller BERT model, PyTorch Lightning. I don't have enough space in my console right here, but it would give you a nice overview over your model, how many parameters it has, what kind of layers it has, and so on. So we also need a validation step if we have a validation data loader. Validation step, and we need the validation epoch end function. So usually in training, you don't really care about epochs too much because you just have mini batch after mini batch. But in validation, what you want is kind of one single metric across your entire test data set or validation data set. And therefore, you sort of, in the validation step, you'll just kind of output things. You output local things per batch. And then in the epoch end function, you aggregate them into one big number. So we'll just put things into each thing. So I'm pretty sure we're going to end up in the validation step first, because especially if we do this debug run, it tries to run a validation first at the very start of training. So we can look at a batch right here. So what's a batch? The batch seems to be a dictionary. If you look at its keys, we have label and input IDs. Okay, so that's pretty cool. So if we go for the input IDs, that gives us a tensor, and the tensor is of shape 8, which is our batch size, and 32, which is our sequence length. And we should be able to pretty much input that into the BERT model that we created. Boom. Okay. And what do we get out? We get out a tuple, and the first entry is going to be, this looks like logits. All right. Okay. Let's check the shape. And this is 8, so this is our batch size, and 2 is the logit. So one for the negative class and one for the positive class. And this we can basically input into a cross entropy loss given our labels. So we also have our label here. And our label is all ones. Nice. Is this maybe sorted? Is the dataset sorted into good and bad things? Because that would be bad. In any case, so what do we have to do? So in the forward method, we get the input IDs. Let's just say we get the input IDs, and we run this through our model. And we can actually construct a mask here, and the mask is going to be wherever the input IDs are not 0. And that as a, what does it need to be? So this attention mask is going to be a float tensor. Okay, so we'll put it as a float tensor. Cool. Right, like this. So our logits are going to be that. And yeah, tuple with one entry, so the comma here is important. We're going to return the logits. So this is our forward function. So in the validation and the training step, the first thing we got to do is we got to call this forward function with the input IDs, and these of course are in our batch like this. So these are going to be our logits. And then in the validation, what we want to do is we first of all want to compute our loss, right? So we have to construct this up here in the init. We can actually fold this prepare data. Loss is going to be a cross entropy loss. Yes, that exists. With reduction, I like to put reduction none. I don't think there's like a deprecated reduce, and there is like a reduction where you can put mean or something. I like to not reduce the loss at first, because then I can use the same thing for validation and training. So in the validation step, I just want to compute my loss right here with self. So loss, and we'll have to cheat a bit. So look up the cross entropy loss, and come on. Okay, where is the cross entropy loss? Cross entropy loss, it takes, yes, it's reduction. Ha, ta-da. And so the input to the function that we construct is going to be first n by c, first the input and then the targets. So first the logits and then the targets, right? Criterion that combines log softmax and NLL loss over a single class. Nice. Okay. Cool. So first logits and then labels. Label. Okay, that's our loss. So if we check out what our loss is going to be, it's probably going to be an vector of size 8, because we have reduction none. Loss, yes. See, vector of size 8, very nice. So we can just basically return, I'll say we can return this loss just as is. And then in the validation epoch end, the outputs here is going to be a list of, and every entry in the list is going to be one of these validation steps for one batch. So we can aggregate those. So losses will concatenate them, since they're going to be chunks of 8. Outputs at the dimension 0. And then we can calculate the mean, right? So we can do that. And then we can, oh, no. We need to do more. We also want to know the accuracy, right? So the accuracy is going to be whether or not the logits.argmax is equal to the label. So the accuracy for each sample is going to be that. It's either going to be 1 or 0, and we want that as a float. So here, let's output a dictionary with loss and accuracy. All right, excellent. So here, then we can aggregate. So the loss is going to be, and I like to have like a construction here that aggregates this still. So we go out loss for O in outputs. So these are now going to be entries. Each one is going to be a dictionary, right? So our losses, we have concatenation, mean. Okay, our accuracy is going to be the same thing for the accuracy. Nice. So our output here is going to be a dictionary. And I think in PyTorch Lightning, if you put validation accuracy, so like valac, it selects the model according to this, but I'm not sure. So also in PyTorch Lightning, I can now output this here, but also if you have a log entry, it will forward this to the logger, which we can actually do and make a TensorBoard logger out of this. So what have we done? We have, first of all, set up the validation step. So the PyTorch Lightning is going to run through the data loader. For each batch, do this. So we forward it through the BERT model to get our logits, and then we compute our loss by the cross-entropy loss of the logits and the labels. We also compute our accuracy by seeing how much the logits agree with the labels, or the maximum logit. And then we aggregate all of this over the entire epoch and output that. Now let's set up a logger. So for the logger, we can put this, I think, in the trainer here. PyTorch Lightning logger dot, and I think there is a TensorBoard logger. Pretty sure. PyTorch Lightning, is there TensorBoard? No, PyTorch Lightning logger. I'm pretty sure that exists. That's not the newest version. I hate these old docs. So latest. Oh, come on. Oh, this was called logging logger. Arrgh. Loggers. TensorBoard logger right here. Nice. So our saved here is going to be called logs, and then what do we want? We want the name IMDB, and there's also this version thing where if you don't put version 0, it will just make a new kind of folder each time, but I guess we delete the logs anyway. We delete the logs folder at the beginning, so we don't have this problem. But I generally like to overwrite my logs and not make new runs. But if you like something different, that's, you know, fine. All right, so let's run this again. And we're cool. This is the BERT configuration that we loaded. And then we have no attribute logger. PyTorch Lightning loggers. Okay, again, loading the weights, very cool, blah, 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 blah. And we're in an IPython shell. And do we have an IPython shell remaining? Only in the training step. Okay, so we're at the training step right here. And we can actually, we can check whether or not, now we have lightning logs and logs. Okay, so these appear to be our TensorBoard logs. So we are maybe able to run a TensorBoard here later. Let's run it. Logs. We don't have TensorBoard? Okay. Oh yeah, I've uninstalled it because I was angry at it. Oh, come on. What's going on? I don't have TensorBoard. I should have TensorBoard somewhere. It's like in local bin or something. Local bin. No, it's not in local bin. We'll find it. We'll figure it out. How to get a TensorBoard. Maybe we need to install TensorFlow. Well, that's going to take a while. Okay, so back to the training step. In the training step, we basically need to do the same as in the validation step. So we'll need to forward our batch through the model. But here we don't need to compute an accuracy, but we do need to compute a actual batch loss that we can back propagate on. Now, in the training step, you can either specify how you back propagate per se, or what you can do is you can just output this log loss attribute, and then PyTorch Lightning will basically do the back propagation for you. We have the tensor board now, please. All right, there we go. And we can put this into a different thing right here. Git NLP demo. Yes. Okay, so this is running. And if everything goes correctly, 6, shaboom, we have a tensor board. Okay. So we need to forward our training step, and we need to calculate a loss for the batch. So these loss here, we do the same thing, but here we call mean on it. So this is the mean loss from this batch, and we can now return the loss right here. And we can also, in the training step, you can also output a log dictionary, and we'll output the loss again here in order, so this is going to be our training loss that we output right here. Let's call it train loss. And this also will go into the tensor board. So if we run this right now, we don't have an IPython shell. Simply by outputting this loss attribute, we already instruct PyTorch Lightning to now run backprop on this loss using the optimizer that we have defined. Okay? And by outputting the log, we instruct it to put this into the tensor board. So now we have a scalar entry, and you can see this, it only contains the valid, no, it contains everything. Very cool, very, very cool. So let's remove the debug flag, and we'll just see what happens. So to recap, right, we have, oh, now it goes, see, epoch 1. Epoch 2, go, 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 go. Ah, very cool. What we've done is we've set up this PyTorch Lightning module. It needs a bunch of functions, but in the init, we've basically just set up our BERT model from the Huggingface Transformers library. We've loaded in a pre-trained BERT model that we're going to fine-tune. The main thing that the PyTorch Lightning module needs is a training step function where you define what it should do with the data and this data loader function. So in the data loader function, we've loaded up a data set and we basically specified the batch size. This is very easy. Where does the data set come from? We do it here in prepare data. This is a special function in PyTorch Lightning that's basically called after the init, but before anything else runs. And here we are loading this data set from the NLP library. And this is kind of the magic part. We specify the split and the size that we want inside of the string. And you can do this in % or in a number of samples that you want. I'm sort of sure you can do more things, but I haven't explored that. Then we run map on the data set in order to tokenize it, and that's right here. And we use a tokenizer again from the PyTorch Lightning. And just run this encode function. This is very simple. Like, how complicated was this just like a year ago? Crazy. Then we need to put set format, and set format tells the dataset how it needs to output its samples, and we tell it please output torch tensors, and we want these columns right here. And we make a train and a test dataset with from the train and test split accordingly. So we have this goes into a data loader. PyTorch Lightning will take the data loader and run training on it using this train step function. In this train step function, we get a batch, In the batch, there are these two columns that we specified previously, input IDs and label. The input IDs will put through the forward function of the model itself. This is the forward function. We'll construct a mask and run it through the model. We wouldn't actually need to construct a mask, but okay. And we get back the logits of the classification. And then we run this through a cross entropy loss, get the mean of the batch, and there we go. In the validation step, we do the same thing, but also calculate the accuracy, but don't calculate the mean. We want to keep it per sample, and only at the end we want to concatenate everything and calculate the mean. If we've done everything correctly, you see right here, our train loss goes down, down, down until it is almost zero, because we've just, and the validation accuracy is super high. Is this because all the labels are equal? Like for real? Okay, so we'll do something else. We'll make an integer with %. And this was 5, right? So we loaded 5% of the data set. But let's load some more. And this might take longer, but let's load 50% of the data set and just see what happens. No. Present. I called it present. Very good. So we'll load up 50% of the data set, and we'll do the same thing, and we can track in real time what happens in TensorBoard. And unrecognized instruction format. Okay. Ooh, can we make a format string in a format string? This is nasty. Does it work? Please work. We can make a format string in a format string. Absolutely bonkers. Okay, so it takes a little bit longer, and you could actually, I think you can speed this up, this mapping of the data set. Maybe you can stream it. I'm pretty sure you can batch it. You can do a batch processing of this. But for our case right here, we think it's enough. So it was like what, 1,200 if we had 5%. So now it should be something like 12,000. So let's continue with the recap of what we did here. We have the train data set, the validation data set, and yes, so we have everything like this. The configure optimizers, you can put an optimizer, you can also put a learning rate scheduler if you want to. And then in the main function, we load this PyTorch Lightning module, and we specify a trainer, and the trainer, we tell it, you know, the max epochs and so on. And we set up the logger, and we just run fit on this model. And this runs epochs of the model, and after each epoch, it does a validation epoch and minimizes our loss. Very cool, very effective. So now, please, if you would. All right, here we go. This is my laptop training BERT. Okay, we don't seem to make too much progress. Let's check the TensorBoard. Training loss goes down, training loss goes to 0. I have the sneaking suspicion that this is not entirely shuffled. So, is there like a shuffle thing? Because this seems a bit fishy. This IMDB dataset right here. It just seems like, you know, we could use a bit of shuffling, because all the labels, yeah, the training loss instantly goes to 0. So maybe it's not. Can we shuffle here Let's look at the load dataset function. Brum, 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 brum. Load dataset batched. No, keep in memory. No, none of that. Okay. This does not seem to go to continue. Right here, datasets, NLP, datasets. I hope here we should find this load dataset somewhere. Builder, features, load. Load dataset. Da-da-da. Split. Can we not shuffle anywhere? We'll search. Shuffle. Builder. Okay. So generate examples. This function pre-processed examples. Key will be hashed. Okay, we are not able to shuffle this just like that. But I hope this at least gives you an impression. I guess if you were to take the full data set and map it, then it would actually work. We'll just try again with 10% of the data, just to see it go down. Tensor board. See, this is now good because we always delete the logs folder. We don't have any remnant old TensorFlow logs. All right, come on. Come on. So 10% should be, yeah, about this. About this. Okay. Train loss. Looking good. Looking good. So far. Look at these models. How large is that? How large is the BERT base case? Huggingface pre-trained models. Pre-trained models. BERT base on case. That's the one we have. 12 layers. 110 million parameters. Easy. Easy. Oh, no. It's too large. Training loss goes to 0 again. Okay, so we've determined that this data set very probably isn't entirely shuffled. It might just have all the good labels first and all the bad labels last. And yeah, just to confirm, let's confirm this right here. Let's go with 100%, but let's put an IPython shell down just before we map the data set, so we don't have to go through the whole mapping procedure. Actually, that would be here, right? Yes. Can we not map this asynchronously? Map. I might be doing something really wrong with this library, but I think that's how it should go. So map def map right here. We can do batched. We could do batched. And then I think Huggingface has a function to encode batched encode. Batch encode. Encode batch. No. Let's go to the tokenizer. Shabadabum. Build inputs, create token type IDs, get special token mask, save. Where is encode? Right here. Can we have batch encode? Build inputs. No. This might be it. Batch encode. Yes, there is a batch encode where you have batches of these things. So, okay, what if we do the -1? See, here's the label 0. I'm pretty sure. I'm pretty sure. Batched true. Let's do that, and in our function here, we'll say batch encode. So let's see how fast this is with 100%. BERT tokenizer has no, but we just had batch encode. Oh, but this might be, we have batch encode plus. Batch encode plus. Or text pairs. Okay. We need this batch encode plus. But then that gives us a dictionary, right? This gives us a dictionary with the fields input IDs right here. So like this. How about that? And then we still might want to limit the actual data set once we have mapped it, because we need to train on it as well. But I just want to see how fast this batch encoding is. Yes. Okay, reasonably fast, but it takes like 3 minutes. Yeah, so we won't go on here. I will put this as is on I'll put this as is on GitHub, and I hope you can profit from that in any way you want. The Huggingface site has a tutorial on Squad where they also use the metrics. So they have basically these predefined metrics like bleu or rouge, I think. And you can just use them as you use these data sets. So it's very, very, very convenient to work with these things in NLP. So NLP has come a long way. Absolutely invite you to check out the transformers and tokenizers and NLP repos. And with that, that's it for me, I think. I hope you enjoyed this. Again, leave a comment if you see improvements or if I maybe should edit this a bit more. I thought the entire process of just going through and making mistakes would be entertaining to some. All right, bye-bye.